Chapter 21 is about the accuracy of percentages. So far we've looked at problems in which we know the population parameter, or in other words, what's inside the box, and we're trying to draw conclusions about the sample. But in general, we actually go the other way. So what we're going to want to do is we're going to want to use the sample to draw conclusions about the population. So if you remember, the population is everything that we could possibly be interested in. So like everyone in the US or everyone in Utah, that's your entire population. But because it's too expensive or time consuming, we don't actually collect data on everyone in the population. Instead, we just collect data about the sample, a smaller subset that's our sample, and then we try and use the sample data to estimate or draw conclusions about our population. Okay, so once again, we're going to use our sample to draw conclusions about the population, is usually what we're going to be doing. Now our sample, we can relate that to the draws from the box, and the population represents the entire box itself. And this is called inference when you use the sample to draw conclusions about the population. So for example, if we don't know the population percentage, we're going to estimate it with the sample percentage. When we use a sample to make estimates about the population, we don't know how many of each number are in the box. And so we might know what's in the box if it's zeros or ones or something else, depending on what we're doing, but for percentages it'll always be zeros and ones. Okay, but we don't know how many tickets of each. We don't know the exact ratio of what's in the box. So instead, we're going to use the sample data to estimate what goes in the box. And to do this, we pretend that the population, or the box, is just like the sample, or the draws. And from there, we can estimate the box average and standard deviation. And just as a note, your sample percentage is going to be off from the population percentage just due to chance error. And the standard error tells you how much you're likely to be off by. Now as a remark, remember that your standard error of the percentage is equal to the square root of your population percentage times 100% minus the population percentage over the sample size. So how does this come into play now? So in this example, USU has 23,000 students. Suppose we take a simple random sample of 250,000 students and find that 130 of them are female. So what happens is, once again, remember this box, the box itself is your entire population. Or that would represent all of USU. And then from that box, we draw a sample. So we took a sample of 250 students, so we reached in the box, drew a ticket, reached in the box, drew a ticket, and we did 250 draws. Now notice inside the box, I do know that there's 23,000 tickets total, but it didn't tell me how many are male or how many are female. So I don't know the ratio of these tickets. And so we don't know how many males or females, zeros and ones, are in the actual box. So what we do is we lift ourselves over that hurdle by our own bootstraps, is the term we like to use. And to do that, basically we just pretend that the box looks just like the sample. Now pretend is a key word there, but we pretend that the box looks just like our sample. So number one, let's estimate the percentage of USU students that are female. So our best guess for the population percentage is the sample percentage. To find the sample percentage, you say, okay, 130 out of 250 were female. Is the sample percentage, which is 130 divided by 250, which gives me 0.52. And if I want it to be a percentage, you just times your decimal by 100%. So it gives me 52%. So my best estimate for the percentage of all USU students who are female is 52%. So once again, your best guess for your population percentage is the sample percentage. Now number 2, find the approximate standard error of the percentage. Well, to find standard error, a percentage is the square root of your population percent times 100 minus your population percent divided by the sample size. Now there's a slight issue here. We don't know the population percentage. Right? That's why we're doing this. We don't know the population percentage. So instead, we will estimate it with the sample percentage. So I'm going to do a wavy equal sign to let you know that I'm just kind of estimating it, that this might not be exactly correct. We're going to estimate it with the sample percentage times 100 minus the sample percentage divided by the sample size. Once again, we have to estimate it because we don't know the population percentage. But our best estimate of the population percentage is the sample percentage. So my sample percentage is 52 times 100 minus 52 divided by my sample size, which we did 250 draws, or a sample size of 250. So this gives me 3.16%. And so what does this mean for us? It means that we estimate that about 52% of the USU students are female, give or take about 3.16%. Okay, so that standard error still tells us kind of what our give or take is, or how much we're likely to be off by. And just keep in mind that your sample percentage is almost always going to be different from your population percentage just due to chance error. And how much do you estimate that it's going to be off by? We estimate that our sample percentage is likely to be off by about 3.16%. Because it's always likely to be off by about the standard error. Now there's this interesting phenomenon where every time I take a different sample, I'm likely to get a different sample result. So in example 219, Spencer takes a different simple random sample of 250 students and finds that 121 are female. So he's going to estimate that about blank USU students are female, give or take about what? Okay, so first of all, what is his guess for the population percentage? So he's going to estimate population percentage by the sample percentage, which is, let's see, 121 out of 250. Put that in your calculator, so 121 divided by 250, and that gives me 0.484, times it by 100%, so we get 48.4%. So he estimates that about 48.4% of USU students are female. But now he needs a give or take. He needs to know how much he's likely to be off by. So the standard error for the percentage, once again, is equal to your population percent times 100 minus your population percent divided by the sample size. Now I'm going to do an approximate sign, not equals, but approximate, because I don't know the population percentage, but I'm going to estimate it with my sample percentage, which was 48.4. So this is going to be 48.4 times 100 minus 48.4 divided by 250, which is 3.1606%. So he estimates that about 48.4% USU students are female, give or take about 3.1606%. So Spencer took a different simple random sample, so he got a different estimate of our population percentage, as well as a slightly different standard error estimate. Now in our next example, Hazel takes yet a different simple random sample of 250 students and now finds that 153 are female. So we're going to go through the same thing for Hazel. So she's going to estimate the population percentage as 153 divided by 250, and we'll times it by 100% to get a percentage, which is 61.2%. And now find the standard error, and it's going to be about, since I'm going to have to estimate the percentage, 61.2 times 100 minus 61.2 divided by 250, which is 3.08%. So what does this mean? She estimates that about 61.2% of USU students are female, give or take about 3.08%. So 2 remarks here. So each different sample was giving us a different sample percentage. So we took 3 different samples and we got a different sample percentage each time, and hence a different estimate of our population percentage. But our next remark tells us our population percentage is fixed. So we don't actually know what the true population percentage is, but it is a set specific value. I just don't know what it is. Our sample percentages, though, they do change from sample to sample. So when I'm getting these different estimates of 61.2 or 48.4 or 52%, those estimates are changing. That doesn't mean that the overall population changes, because it's not changing. That's a fixed constant. What does change is my estimate from sample to sample. So for our next example, USU has 23,000 students. Suppose we took a simple random sample of 250 students and find that 130 are female. So from example 218, we estimated the percentage of USU students that's female is 52%, give or take 3.16%. So that's just from example 218. So in other words, we estimated that the population percentage is 52%. And then we estimated that we're likely to be off by about 3.16%. So just another way to phrase it. So we estimated that we're likely to be off by 1 standard error. Now we're often interested in increasing our confidence of our estimate. So instead of just using our estimate plus or minus 1 standard error, we might go out to plus or minus 2 standard errors. By the time we go out to plus or minus 2 standard errors, we feel pretty confident that we're going to have the correct range. So if we go out to plus or minus 2 standard errors, we would call this a 95% confidence interval. So this is very important, very big deal in statistics. It's the 95% confidence interval for the percentage of all USU students that are female. So let's find this 95% confidence interval. So 95% confidence interval is going to be our estimate plus or minus 2 standard errors. So in our case, our estimate was 52% plus or minus 2 times the standard error, which was 3.16%. So when I do, or let's simplify first a little bit, so 52% plus or minus 6.32%. So if I do the subtraction first, 52 minus 6.32, that's going to give me 45.68%. Now if I do 52 plus 6.32, then I get 58.32%. So this is a 95% confidence interval. Congratulations, we just found our first confidence interval, something that's very, very important to statistics. Now, what does it actually mean? So I'm going to write this down. We're going to write it down many times. This is something you need to memorize of what a confidence interval means. So what it means is we are 95% confident that the population percentage, or the percentage of all the USU students, now I'm capitalizing that all because that's very important, because I'm telling you again, this is my population percentage. This is the percentage of all the USU students. So the percentage of all USU students who are female is somewhere in this range that we just found. So it is between 45.68% and 58.32%. So once again, we're 95% confident, so that's how confident I am, that the percentage of all the USU students who are female is somewhere in this range, somewhere between 48.68 and 58.32. So I don't know what the exact population percentage is, but I'm very confident that it's somewhere between those two numbers. So a little theory, a confidence interval, we like to abbreviate with a CI, is used when we want to estimate an unknown population parameter. Now, do you remember what a population parameter is? So population parameter, a parameter is a numerical value, something that we calculate for a population. So in other words, a confidence interval is used when we want to estimate some unknown value for our population, and we estimate it using our sample data. The interval gives us a range of plausible values. So this confidence interval we found in our last example of 45 to 58%, that's our range of plausible values for our unknown population percentage. And it also gives us a confidence level. So how confident were we? We were 95% confident. That's how confident we were. 95% confident that our range, this range, contains the true value of the population percentage that we were estimating. So there's different confidence levels that you can do. If you go out one standard error, so your sample percentage plus or minus one standard error, then we'd call that a 68% confidence interval. If you want a 95% confidence interval, you have to go out two standard errors. And if you want a 99.7% confidence interval, you have to go out three standard errors. Now those numbers should look familiar. That's because it comes back to the normal curve, where if you have your normal curve, you have your expected value, and if you go out one standard error in either direction, that should contain 68% of all of your sample percentages, and two standard errors should contain 95% of your sample percentages, and three standard errors should contain 99.7% of all of your sample percentages. And so once again, if you want a 68% confidence interval, you got one standard error, 95% you got two standard errors, and 99.7% you can go out three standard errors. So let's try an example. A researcher in education in Utah takes a simple random sample of 200 Utah high school seniors and finds that 69% of them plan to go to college. Find a 95% confidence interval for the percentage of all USU high school students who plan to go to college. And we're going to write our conclusion in context of the real world problem. Our first step is we need to know, we want 95% confidence interval, so we need to know our sample percentage and our standard error. So that's our first step, find those two things. So our sample percentage is, let's see, out of our sample of 200, 69% plan to go to college. So my sample percentage is 69%. You also need to know your standard error for your percentage. Now the formula is population percentage times 100 minus population percentage divided by the sample size. But once again, I don't know my population percentage. All I know is my sample percentage. So we can estimate it using the sample percentage. So we can do our sample percentage times 100 minus the sample percentage divided by the sample size. Now this is the square root of our sample percentage is 69, so 69 times 100 minus 69 divided by my sample size. We took a sample of 200 Utah seniors, so my sample size is 200. And this gives me 3.27%. So we have our sample percentage, we have our standard error. Now I can find my actual confidence interval. So my confidence interval, once again, is your sample percentage plus or minus 2 times the standard error for your percentage. We got 2 standard errors because we want a 95% confidence interval. So it's going to be 69% plus or minus 2 times our standard error of 3.27%. So 69% plus or minus 6.54%. So this gives me 62.46% to 75.54%. That is my 95% confidence interval. And of course, what does this mean? And write it in context of the problem. So we are 95% confident that the percentage of all the Utah seniors who plan to go to college is between 62.46% and 75.54%. So once again, we don't know what the percentage of all the Utah seniors is, but we estimated it as 69%. But we know that we're likely off by a little bit, and so if I go out 2 standard errors, I can now say that I'm 95% confident that that true population percentage is somewhere within this range between 62 and 75%. Now, what do confidence levels mean? So this is the most important part of what we're doing today, is what do they actually mean? Because yes, a computer or mini calculators will find the confidence level for you, confidence interval for you. What you have to know is how to actually interpret it and what it actually means. So in a previous semester, we wanted to estimate the percentage of red M&Ms for all the M&Ms in this huge jar. So each person took a sample of 70 M&Ms and found the percentage of red M&Ms. And the results are in the table below. So we have each person. So here are people and their sample percentages. So one person got 12.3%, another one got 15.9%, one person got 8.9%, 14, 18, 11, 14, 8.1. So notice people are getting very different sample percentages. And then they all had to estimate their standard errors, and notice that even the standard errors are changing because they're based on the sample percentage, which was changing. Now after they found the standard error, they all found confidence intervals. So one person went from 4.4 to 20.2, this person's like 5.8 to 22.4, 15.2 to 36. So notice they're all getting different confidence intervals. So let's actually skip down below and answer a couple questions and then come back up. So first, did each person get the same percentage of red M&Ms? Well, our percentages were from 12.3 to 8.1, 21, 25. Obviously, not everyone got the same percentage. Okay. Did each person get the same confidence interval? Well, no, all of their confidence intervals are different. And their confidence intervals are all different because they all got different sample percentages. So their confidence intervals were all different because they started with different estimates or different sample percentages. Now, usually we don't know the value for the population percentage, so usually the exact value is unknown. But I was able to count all the red M&Ms in the entire jar. And I found that the true percentage for all of the M&Ms in this jar was 14.5%. So the question I'm asking you is, do each of these confidence intervals, do they contain the true value of 14.5%? So person 1 went from 4.4 to 20.2, and they were 95% confident that the true value was inside that range. And 14.5 is in between 4.4 and 20.2, so yes. And 7.2 to 24, that contains the true value 14, so yes. 8.2 to 26, that contains 14, yes. 2.1 to 15.7, yes, that still contains 14, just barely, but it does. 2.6 to 16, yes. 7 to 24, yes. 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 In fact, as I go down, most of these seem to contain that value of 14.5%. Until I get to this one right here. So these are all yeses. Until I get to 15.2 to 36. That one did not contain the true value of 14.5. So this one was a big fat no. Then 6 to 23, yes, that one contains 14, yes, and yes, barely. So, did all of the confidence intervals contain the true value of 14.5%? No, but most did. So not all of them contained the 14.9%, but most of them did contain the true value, which was what we wanted. Specifically, how many of the 95% confidence intervals contained the true value of 14.5%? Well, let's go up and count. There were 16 people, and all but one contained the true value, so 15 out of 16, or let's see, 15 out of 16 times 100% gives me 93.75%. So 93.75% of the confidence intervals, or of the 95% confidence intervals, contained the true population percentage. So let's continue this example. I had a computer simulate drawing 100 different samples of these M&Ms and finding the percentage of red M&Ms, and here are our results. So what they do is they draw in these confidence intervals for us. So each line represents a confidence interval. The dot in the middle represents the population percentage, the sample percentage, and then you extend on either side, the little green or red lines extend out to standard errors. The line down the middle is the true value of the 14.5%. Now notice most of these confidence intervals do contain the true value of the population percentage. Also notice that your sample percentages aren't all the same, which is why the dots in the middle vary, and then also why the confidence intervals vary, because they're all based on the sample percentage. And most of these confidence intervals contain the population percentage of 14.5%, but some of them don't. So this one doesn't, this one doesn't, this one, or this one. So all of those red ones are ones that don't contain the true population percentage. So like this one, this one, this one, and this one. So number 5, there are 95 out of the 100 confidence intervals. So I did 100 confidence intervals, and 95 of them actually covered the true population percentage of 14.5%. So how many intervals didn't? There were 5 that didn't, or 5 out of 100 times 100% gives me 5%. So 5% that didn't. But in part 5, there were 95 of the 100 that did cover it, so that's 95% that contained the true value. So, why do you think we call it a 95% confidence interval? The reason why is that because 95% of all the possible confidence intervals actually contain the true value. And let's write just a little bit more. Okay, so let's just write ourselves a note. So because I get a different sample percentage with each different sample, I get a different confidence interval each time. So there are many different samples we could choose, and each one gives a slightly different confidence interval. So of all the possible confidence intervals we could end up with, 95% of them should contain the true population percentage. So one more example. Lemons are premium grade, table grade, or juice grade. A farmer takes a simple random sample of 500 lemons from a large crop and finds that 75 of them are juice grade. Find a 95% confidence interval for the percentage of juice grade lemons in this crop. Write your conclusion in terms of the real world problem. Let's see what we have here. He takes a sample of 500, so my sample size is 500. My sample percentage is equal to, let's see, there were 75 of them out of 500. Times it by 100%, so you can get an actual percentage, and that gives me 15%. We need to calculate our standard error as a percentage. So it's the square root of your population percentage times 100 minus the population percentage over the sample size, which is equal to, or not equal to, approximately equal to, or close to, because once again, since I don't know the population percentage, I'm going to estimate it with the sample percentage. So it's going to be close to 15 times 100 minus 15 over my sample size of 500. So 1.6%. Let's just write ourselves the little note. Since I don't know the population percentage, I estimate it with the sample percentage. Now let's find our actual confidence interval. So your confidence interval is equal to your estimate, in this case our sample percentage, plus or minus 2 standard errors. So our sample percentage was 15%, plus or minus 2 times 1.6%. So if I do 2 times 1.6, that gives me 3.2. So we're 15% plus or minus 3.2%. And if I do the minus first, I get 11.8%. And then if I add it, 15 plus 3.2, I get 18.2%. That is my 95% confidence interval. And finally, what does this mean? We need to write it in context of our problem. So we are 95% confident. First you tell me how confident you are. That the percentage of all, that all is very important. This is not just the percentage of the sample, but the percentage for all the lemons in the crop. Percentage of all the lemons in the crop are, let's see, the percentage of all the lemons in the crop that are juice grade is between 11.8% and 18.2%.